continuity, you can't have a removable discontinuity, because that's called a removable discontinuity, aka not continuous, aka not continuity. Okay? Jump discontinuities are also discontinuities. So continuity happens when from the left side and the right side you approach the same thing and the value of the function is the same. Okay? So we have, does the limit x approaches c of f of x exist? If so, where? So does the limit exist on these graphs? Does this one have the limit that exists at c? Yep. Because from the right and the left it's approaching the same thing. Yep. What about this one? Yep. What about this one? Yep. What about this one? Nope, that one, the limit immediately doesn't exist. What about this one? No. So what we're going to say here is the limit as x approaches c of f of x. For this one, it equals f of c, correct? Can you see that? We're just going to say if the limits do exist. So for this one, we'll just say the limit as x approaches c of f of x exists. I'll explain more after. What about this limit? It exists. This one, the limit as x approaches c of f of x does not exist. And this one, the limit as x approaches c of f of x does not exist. So the moment that your limit doesn't exist, the graph is done. It's not continuous at that value. Correct? Because if the limit doesn't exist, we know that the graph has a jump discontinuity. So it immediately can't be continuous. You can pick your pen up. Continuity states that from the left I come into the graph, add the value, I just close the dot, and from the right I carry on. Right? I don't have to pick my pen up at all. If you pick your pen up, it's not continuous. If you can draw along the way, fill in the dot, carry on, it's continuous. So the moment that these don't have a limit, these two functions are immediately not continuous. So if the limit doesn't exist, the function's not continuous. Done. I don't even have to talk about the actual value. That immediately kills the fact that that graph is not continuous. Okay? So that's one rule. That it has to have a limit. Okay? If it doesn't have a limit, it doesn't exist. Then we have to look at what the actual value of f of c is. Because if f of c is not the same as the limit, the graph's not continuous, correct? So what does that mean? That means if I draw a graph like this, and then I have an open dot and I carry on, and at f of c I had to lift my pen up and put a dot here, that's not a continuous graph, correct? I would be drawing, open dot, close the dot. Like if I pick my pen up, that graph's not continuous. We agree? So the only graph that's continuous here is actually number 1. Because the limit as x approaches c equals f of c. This one, the limit as x approaches c of f of x does not equal f of c. And this one, it for sure doesn't, because f of c doesn't exist. So these are not continuous. So if you can prove that a limit doesn't exist, or the value of that function at c does not exist, the graph can't be continuous, correct? Because the only way a graph can be continuous is if from the left and the right it's approaching the same value, and at the value it's the same value, so you can just carry through with your pen. So to prove continuity, we have to prove that the limit and the value are the same. The moment a limit doesn't exist, or the moment a value doesn't exist, or the moment they don't equal, the graph isn't continuous. So these are all the different reasons how a graph would not be continuous at that value. Now, a graph can be continuous every single other place, but the entirety of the graph is not continuous. Okay? So here's our definition for continuity. A function f is continuous at a number c if the following three conditions are met, and these three conditions have to be met. F of c is defined, so that means you actually have a coordinate, a closed dot, at that x value, correct? Whereas up here, look, I had a limit, but I didn't have a closed dot at c, correct? I had an open dot, so the f of c didn't exist. So f of c has to exist, the limit has to exist, and then if they both exist, they have to be equal to each other. These are the three conditions that have to happen. So if ever I ask you to prove that something is continuous, you have to tell me what f of c is, you have to tell me what the limit at c is, and then you have to tell me that they're both equal. That's how you prove continuity. Because the moment the limit doesn't exist or the value at that dot doesn't exist, you're done. It's not continuous. If both of them don't exist, you're super not continuous, but you only need to have one. Super not continuous. So, we want to prove continuity. We want to prove that this parabola, this quadratic, this degree 2 function, is continuous at 1. Well, we know it is. Every polynomial is continuous, correct? Yeah. Lines are continuous, quadratics are continuous, cubics, quartics, quintics, right? Every polynomial is continuous. So we know it's continuous, they just want us to determine whether it is. So how do we do that? Well, we first have to do number 1. We have to show that f of c is defined. So it's continuous at 1. So we have to find f of 1. And we have to show them that it actually exists. Okay? F of 1 is 3 times 1 squared minus 5 times 1 plus 4. F of 1 equals 2. Sure? Perfect. Check. Number 1. We have a value for 1. Yay. Okay. Then that's step 1. I'll put a little 1 here to help us out. Step 2, in blue. I now have to prove that the limit exists there. So the limit, as x approaches 1, of 3x squared minus 5x plus 4 exists. Well, I told you that the very first thing you do when you get a limit is you try direct substitution first, correct? If it works, yay, you're done. If it doesn't work, you're going to have to do some algebraic process to try and get it to work. Yeah? Well, this one I can plug right in. It's a polynomial. It's the greatest thing about polynomials. You can always do direct substitution. So the very first thing I'm going to do is direct substitute. And when I substitute in the 1, I don't need the limit word anymore because that just tells me what I'm substituting in. So I'm going to fill that 1 in. And I'm going to get 3 bracket 1 squared minus 5 times 1 plus 4. And I get 2. Shocking, I know. It's not shocking. We filled the 1 in and we just filled the 1 in there. Now some people will say, oh, I don't need to show that. So guys, you do. So that's why I said this lesson is actually not a hard lesson. The hard part of the lesson is convincing you that you actually can show me all the work to get the correct marks. Okay? So you do. You have to show me step 1, that when you fill in 1, it's 2. You have to show me step 2, the limit, that when you fill it in, it's 2. And then to prove it's continuous, you'd say the limit as x approaches 1 of f of x equals f of 1. Therefore, f of x is continuous at 1. Now some people will say, well, I'll just show that I'll just go f of 1 is 2. I'll say the limit is 2. I'll show no work, and then I'll say it's continuous. No. This is the minimum of what you have to show in order to get full marks. Okay? So step 1, show the function's value. Step 2, show the limit's value. Step 3, say if they're the same, and if they are, it's continuous. If they aren't, say not equal to, and it's not continuous. That's it. Not a hard concept. Okay? The next one. Let's do f of 2. And by f of 2, I mean g of 2. Oh my goodness. That's a g. So we're going to do g of 2. Everyone's writing this down. Okay. So we tried direct substitution. G of 2, well, we always do direct substitution. This is direct substitution. 2 squared plus 9 over 2 squared minus 4. So I'm going to get 13 over 0. So what can we say about g of 2? It does not exist. The moment g of 2 does not exist, do we even have to keep going? No. Therefore, the graph is not continuous. The limit would exist if we did the 2, because it's, actually, I don't think the limit would exist. Crushed in 2 ways. Okay. Yep. Absolutely. Yeah, it's math. It's actually math terms in the world. So we're allowed to use certain terms because they're math terms in the world. Like for all, this means for all. We're never using that in this, but in math, that means for all elements in the integers, because that's actually integers, not the I that we use. I don't know why Alberta does. That's integers. So when you go into math, you'll see there's tons of words that mean. Yep. You can't write HA, but you can write DNA. Yeah.
That applies to like all the wording and syntax and what we do. Is that like the same for
Okay. So, try. Give you a few minutes. So this one wants to know if it's continuous at -2, 0, and 2. So the first thing we can do is we can literally plug in f of those values and see if those exist first, right? If they don't exist, then we're done on that value. So that's the easiest way to go about it, right? So let's do f of -2. So f of -2 equals the square root of -2 squared plus 2 over -2 squared minus 4, which gets us 2, no, what is that, 4 of 6, square root of 6 over 0. So f of -2 does not exist. Therefore, f of x is not continuous at -2. Okay. I'm going to do 2 next, because I know it also wasn't going to work, because if I square a negative or I square a positive, it ends with the same value. So I'm going to do f of 2. F of 2 equals the square root of 2 squared plus 2 over 2 squared minus 4, which is the square root of 6 over 0. So f of 2 does not exist. Therefore, f of x is not continuous at 2. All right. So we know that -2 and 2, it's not going to be continuous out, because if I factor that denominator, I get x plus 2x minus 2. So I know that that's going to be actually where some asymptotes will be. Okay, so I know that's not going to work. But 0 should work. So we're going to have more work to do. So we have f of 0 equals the square root of 0 squared plus 2 over 0 squared minus 4. So I'm going to get root 2 over -4. So that's f of 0. So that has a value, correct? And then we have to prove that the limit as x approaches 0 of square root x squared plus 2 over x squared minus 4. So you have to show the actual limit with the equation first, correct? And your second step is direct substitution, which you know will end up being the same as the other one, because that was our direct substitution. So this is going to equal 0 squared plus 2 over 0 squared minus 4. So you get root 2 over -4. And so then we have step 1. we showed f of 0 has a value, right? Step 2, we showed the limit has a value. Step 3 is to state that they're the same. So f of 0 equals the limit as x approaches 0 of f of x. So that's step 1, step 2, step 3. And when that's true, we can say, therefore, f of x is continuous at 0. Now, some people will just read this and say, it's continuous at 0. That's not determining anything. That's just stating a value, right? So we have to show the word. So if the limit crashes or the value crashes, it does not exist, we're done, right? It doesn't continue, it's not continuous. If the limit exists and the value exists, we then have to say that they're the same or they're different to say it's continuous or not. Okay? Okay. We'll have this one, but we're not doing this right now. All right. So this one here says determine whether the function is a piecewise function. Do you see it? Determine whether the function, and great, determine whether the function, good job, Lepp, is continuous at 3. Well, missing. So this one actually is a piecewise function. We're going to have to find the value at 3. We're going to have to find the limit at 3, which actually is going to make us find from the left and the right on this one because we have a less than and a greater than. And then we have to say if they're the same. Okay? So f of 3 is the easiest one. Step 1. Find f of 3. What is f of 3 equal to? Anyone know? 9. This is a coordinate. When x equals 3, y equals 9. Right? That's a coordinate. So f of 3 is 9. Step 1, done. We haven't failed yet because that's not, that's a value, right? It's not, it does not exist. So we have to keep going. Step 2, determining the limit. We want the limit at 3. The catch here is we have a less than and a greater than. Do you see that? The less than covers the limit from the left, and the greater than covers the limit from the right. And then we have to see if they're the same to get what the limit actually is. Okay, so when we have a less than or greater than, we have to do left and rights. So we have to do the limit as x approaches 3 from the left. Which of those equations, the top or the bottom, is 3 from the left? Remember, left and less than go together. So the top one. So we get x squared minus 9 over x minus 3. If I attempt direct substitution, it's going to get mad at me. Right? So I can't do that. I have to do something algebraically to try and find the point of discontinuity, correct? Or that removable discontinuity. So what could I do? Difference of squares, yep. So I'm going to run an equal sign down because it's going to equal the same as the next one. I still have to write the limit because I'm not substituting in. And I get x plus 3, x minus 3. Over x minus 3. And then my problem child, the x minus 3 cancels off. And then I can do direct substitution, correct? And the moment I substitute in, my limit goes away. So I get 3 plus 3, which equals 6. So that's the limit from the left. This equals 6. Now I have to get the limit from the right to see if they're the same. If they're not, the limit doesn't exist. It's crushed. It's not continuous there. If they are the same, we're in trouble anyways, because why? That point doesn't match up with 3 is 9. But you still have to keep showing. So we have the limit as x approaches 3 from the right. We're going to use this one because it's the greater than equation. We can plug in because we have no problems. 3 squared minus 9. And so it equals 0. Therefore, the limit as x approaches 3, what? Of f of x. What's up with it? It does not exist. Therefore, the graph of f of x is non-continuous